SQL Server has to go through several stages whenever an application executes any Transact SQL code. A lot rides on the whole process, including overall database performance, so SQL Server implements many features to make the process as efficient as possible. The process consists of two broad steps: compilation and execution. In a nutshell, compilation prepares the query for execution in terms that the database query processor can understand, with the end result of a query plan. This is analogous to compiling computer language code prior to execution in an operating system. And execution is actually performing the plan and returning any results to the client application. Compiling a query involves three stages: parsing, algebraization, and optimization. The process transforms the logical T-SQL code you write into the physical operators that define the steps that SQL Server will perform to execute the query and return results. And so this shows you a very high-level view of the entire process. When SQL Server receives a batch of T-SQL statements from a client application, which includes Management Studio, it first checks to see if a plan exists in the plan cache for the query. If the query was recently executed by this or another session, then the query doesn't need compilation. The plan is passed to the execution engine, and this process is done. But if no match is found in the plan cache, then SQL Server parses the query to check the correct T-SQL syntax, including the use of valid SQL identifiers for object names, although not yet to verify that all referenced objects exist, as well as it checks the spelling and use of keywords. Then, for each statement in the batch, the query processor sees if there is an existing plan guide and if it's in the cache. A plan guide is an object that you can define to specify a query plan for a query. If there's a match that's in the plan cache, the processor uses the plan guide for that statement and sends it off for execution. If there's no match, the query is parameterized, which essentially creates a version of the query with separate parameters, and it once again checks to see if the parameterized query is in the plan cache. If there's a version in the plan cache, it's again sent to the execution engine. Otherwise, if there's no matching plan guide or parameterized query in the plan cache, the query processor has to go through the process of creating an execution plan for the query. The first step is algebraization, which is also called normalization. This step creates a logical tree, which is sometimes called a parse tree, that represents the logical steps needed to execute the query. A primary task of algebraization is binding, which checks whether reference tables and columns exist, loads metadata about those objects, and adds information about implicit conversions needed. Then, the next step is optimization, which, as its name implies, performs any refinements that can make the execution plan more efficient. Then the plan is added to the plan cache and finally sent to the execution engine. Now, not all execution plans are cached. For example, you can define a stored procedure with the with recompile option, which causes SQL Server to generate a new execution plan every time the code executes. In that case, SQL Server doesn't bother caching the plan since there's no point. And caching execution plans is one of the major ways that SQL Server dramatically increases the efficiency of query execution. Creating an execution plan can be a time-consuming operation. So if most queries can use a cached plan, the server is going to be able to process far more queries. But even if an execution plan for a query is in the plan cache, SQL Server may decide to recompile the query anyway and throw out the old plan. This process is called recompilation, and it occurs for two broad reasons: correctness and optimality. For correctness, the query processor might determine that an existing cached plan could return incorrect results. In that case, it recompiles the statement or the batch. And there are numerous reasons why a plan might return incorrect results, including schema changes. Maybe you've added, changed, or dropped indexes, statistics updates, use of with recompile, changed environment settings, usually set statements, or even an explicit call to the SP recompile system stored procedure. And then with optimality, SQL Server tracks data distributions with statistics, including information about the number of rows in a table, as well as changes to the data in individual columns. The query processor uses a threshold value to decide whether it should recompile a query. Essentially, if the data has changed too much, it's gone beyond that threshold amount, it could affect the choice of the optimal execution plan, and so SQL Server recompiles it. The benefit of recompilation, even though it's a hit against performance, is that a query with an execution plan that's incorrect or suboptimal is likely to perform far worse than a correct optimal plan, and could even return incorrect results in extreme cases. So the performance hit of recompilation is usually well worth the performance benefits. And a nice thing is that in SQL Server 2005 and later, individual statements can be recompiled instead of the entire batch, which is an enormous performance boost for long batches or complicated stored procedures and other code modules that can take some time to compile. It's really important to understand that the query processor is not looking for the absolute best execution plan possible. A complex query might have thousands of potential execution plans that return correct results. And it might take hours to find the best plan that saves mere milliseconds off a query execution time. One of the tasks that the optimizer does is to look for a trivial plan, which has a known and constant cost, involves no parameters, and only uses system functions. An example of such a plan would result from a select star from dbo.customers. Because this query returns all rows and all columns from a relatively small table, this happens to be from the Northwind database, no amount of analysis is likely to find one method of scanning the table that's substantially better in terms of performance than another. There just aren't that many ways to perform this particular very simple query. So if the optimizer finds a trivial plan, it returns that execution plan and does no further work. Now let's talk about statistics that I've mentioned a couple times. Statistics are an important input to the query optimizer. They're information that SQL Server gathers about database objects that help guide it to an optimal execution plan, such as to know whether a query with a predicate, a where clause, is selective enough to be worth using an existing index, or whether one way of performing a step in the execution plan is better or worse than another. Or, more like, one way is better than the other dozens of ways to perform that step. The optimizer has to make these kinds of evaluations and decisions in advance of executing the query, so it makes use of the statistics that SQL Server has gathered on tables. By default, SQL Server automatically creates and updates statistics, and that works fine for most situations. But there are three settings you can use to influence how SQL Server gathers statistics. The first is Auto Create Statistics. This option is set on by default and guides whether the query optimizer creates statistics automatically for the columns in a where clause if those statistics don't already exist. You should only consider changing this setting in extreme situations, since statistics are so important to query optimization. The next one is Auto Update Statistics. This option is also on by default and guides whether SQL Server updates statistics automatically when there are enough data changes that the existing statistics are stale and could lead to incorrect execution plan choices. The only time that you should consider changing this setting is if the process of updating statistics adversely impacts database performance on a busy server, and you want to manually update statistics during server inactivity. And then the third one is Auto Update Statistics Async. This option is off by default, and it determines whether SQL Server updates statistics asynchronously during query optimization. If asynchronous updates are enabled, the optimizer doesn't wait for the updates for the current query that triggered the update, but the updated statistics will be available for later queries, or at least once it finishes recompiling the statistics. Turn this setting on only if you find that queries are waiting for synchronous updates too frequently. And Auto Update Statistics has to be enabled for this setting to take effect. The statistics that SQL Server creates on one or more columns are stored in a binary large object, which includes a histogram that includes the distribution of values in the first column. A histogram is simply a representation of the distribution of ranges of data values in the column. It's just a way of looking at the density of data. If a statistics object covers multiple columns, the statistics object stores additional information about the correlation of data values between the columns, which are called densities. And SQL Server is able to use statistics to calculate the estimated number of rows that a query is going to return. And this is called an estimate of the query's cardinality, which is an important input for optimization. A factor that influences the shape of the statistics histogram is that it's limited to 200 steps, or ranges of data values. So in a large table with many rows and a column that has many different values, statistics won't have information about every individual value that's found within a single column. This is a compromise that balances the complexity of statistics with their usability to guide query optimization. SQL Server provides two primary catalog views and a dbcc command that you can use to obtain information about the statistics in a database. The sys.stats view contains a row for each statistics object that exists for tables, indexes, and indexed views in the database. And the sys.stats columns contains a row for each column that's part of the sys.stats statistics object. And then the dbcc show statistics command returns information about current query optimization statistics for a table or an indexed view. You can use the system catalog views, along with information from sys.tables and sys.columns, to get a fairly readable list of the statistics that exist for all tables and columns in a database. So this code here shows one way to do that. So what it does is it basically joins together all four of those tables. So these sys.stats and sys.stats columns has the information about the stats, and then columns and tables has information about the columns and tables within the database. And I'm going to run this against the AdventureWorks 2012 database. So I'll go ahead and select that and click Execute. And there you can see the information that's returned. So you can see in this particular instance of the database, there's 264 rows. And it lists everything by table, and then each column within the table. So that's the name of the statistics object that's available. The last update date, and this is around the time that Microsoft created the AdventureWorks 2012 database, so I haven't updated it since that time. And then whether it's filtered or unfiltered and so forth. Now, this is a fairly straightforward query. It's just reading different columns from those various tables. But the one thing here might be new is stats date. And that's a built-in T-SQL function that returns the last update date for a statistic object. It takes an object ID and a statistics ID as a parameter, and then returns a date-time value. If there's no statistics for those specified parameters that you provide, or if there's some other error, then the function returns null. So that's a convenient way to get this last updated date right there. And then if you want a little bit more detailed information, you can also use this dbcc show statistics command. So this statement is going to return information about the statistics for the AdventureWorks 2012's sales.sales order detail table, and specifically for this product ID column. And that has an existing index called IX sales order detail _ product ID. So I can substitute a column name in here and various other parameters, but I want to get it specifically for that index. So I can select that and execute it. And as you can see, I actually get 3 result sets back. So this first result set returns a single row. And this has information about the statistics object for the column, including the number of rows in the table, as well as the number of rows sampled, number of steps. Remember I mentioned that there's a maximum of 200 steps in the histogram, so there's enough different values in the product ID to justify using all 200 of those ranges of values. and then some information about the density and key length and string index and so forth. So this information is referred to as the header information, and it's current as of the last time the statistics were updated. Then the second result set, as you can see, returns 3 records. And this is what's called a density vector, and it measures the cross-column correlation. This all density column right here is the inverse of the number of distinct values for each of the key columns that are listed. So the combinations here, product ID and sales order ID, and product ID, sales order ID, and sales order detail ID. And then average length is the length in bytes to store a list of the column values. Each of the columns is an int. Happen to be primary keys of the various tables, so they're integers. An integer in SQL Server takes 4 bytes of storage, so a single column requires 4, 2 columns require 8, and 3 columns require 12. And then this third result set is the histogram itself. So the range high key is the upper bound for each step in the histogram. Now the values of product ID in the table range from 707 to 999 with 266 distinct values. So that exceeds the number of steps that are available, so some of those have to be combined. And if you scroll down, you see a lot of zeros in some of the first rows, but then there's other values in subsequent rows. This, again, is the upper bound for each step in the histogram. Okay, then range rows is the estimated number of rows whose column values fall into that particular step, excluding the upper bound. All right, so these values range from 0, means that there's a single row, because again, it excludes the upper bound, so each of these zeros mean there's 1 within the range, actually. This one has 218, so that's probably a combination of the 717 and 718. And if you scroll down, you see a few others that are ranging from 0 up to someplace in the 200s. And then EQ rows, or equal rows, is the estimated number of rows with a value that equals the upper bound of the step. So the sum of range rows and equal rows is the number of rows that are in that step. And then distinct range rows is the estimated number of rows with a distinct column value within the step, again excluding that upper bound. Okay, so that's the kind of statistical information that SQL Server is going to gather on these various columns. If you elect not to use the automatic update feature for statistics, you can update the statistics for all tables in the database using the sys.sp update stats system stored procedure. This is something you should do only with great caution, particularly for heavily used production databases, because it can take a long time to execute and uses a lot of resources, so it can tank database performance. Do it only with good reason and when the database is not being heavily used. Now you should consider manually updating the statistics only in a few very limited cases. One is that if you're confident that your queries are well written but are performing slowly, update statistics before attempting to change query execution behavior using query hints. Hints permanently affect how a query is compiled and executed, which may adversely affect its long-term performance. Another scenario is when you insert new rows in a table with new column values that can affect what execution plan the optimizer selects, particularly if the number of new rows are too small to trigger an automatic update to the statistics. In this case, the current statistics might not have the correct cardinality estimates for queries, which could lead to an inefficient execution plan. Bulk inserting rows and truncating a table could cause similar problems. But remember, in most cases, the query optimizer can trigger a statistics update, so you'll not often need to resort to manual updates in this case. And then another scenario is when you update a database to a new version of SQL Server. Microsoft refines statistics with each new version, and the new optimizer will make the best decisions for that version of SQL Server with the latest form of the statistics. The bottom line here is that you should rarely, if ever, take control of updating statistics. The default settings in SQL Server do the right thing in virtually all cases. But if you find a situation where there's a problem with query execution, it's good to at least have the option to take things into your own hand. Now there's another kind of statistics that you can use in order to get information about the performance and the work that a query is doing, and that's called statistics I/O. The idea here is that one of the biggest determinants of query performance is the number of I/O operations that it requires. And you can use statistics I/O in order to examine the number of input-output operations. And you can do that by setting this option on. It's off by default. When you execute a query with it set on, you get some I/O information as a message, which indicates the amount of disk activity required. To get the best information for the query, without any efficiencies from data buffered in memory, you should first clear the cache using the dbcc drop clean buffers statement. But this is something that you shouldn't do on a production server unless you really want to decrease performance. So let's take a look at how you can use set statistics I/O. Here's some code that demonstrates using statistics I/O. This is going to use a query with the AdventureWorks 2012 database. So I first of all execute dbcc drop clean buffers and then set statistics I/O on. So once you do this, once you set it on, all subsequent queries within this current session is going to return the I/O information until you turn the option off. And so that's why I include that off item right there. Okay, so I'm going to execute all of this as a single batch. Execute that. Whoops. Invalid object name. Oh, I didn't change the AdventureWorks. Helps to use the correct database. And execute that again, and there we go. Okay, so this is the results of the query. So it's just returning some information from the product table that's linked to the sales order detail. But here's where you get the statistics information. First of all, there's a message saying that the dbcc execution completed, because there are some operations with dbcc that can take quite a bit of time. Okay, so here's the statistics itself. So it says table sales order detail. So that's one of the tables that's involved in the query. The scan count is 15. And really the most important information is right here, the logical reads and the physical reads. Logical reads is the number of data pages read from the data cache. And that provides an estimate of the effectiveness of a query. And then physical reads is a measure of the actual pages read from the disk required to execute the query for each table. And so if those numbers are inordinately high, it may mean that you have something going on with your query that it's doing excessive disk thrashing. Okay, and then there's various other settings you can see over here, read-ahead reads, large object logical reads, large object physical reads, large object read-ahead reads, and so forth. And you get that for each of the tables that's involved within the query.